Okay. Questions? Okay, so far I'm the only one asking questions around here, so that's my prerogative. Okay, and I'm kind of getting sick last week kind of threw me off my whole schedule a lot of ways. So I'm a little delinquent in getting the previous assignment back to you. But I posted a new one, so I don't like to do that, but I'll take one for the team in that. Okay. So what we're doing is, having established that we can use the same kind of event logic, the language of events to model things that move around. And ironically, I hope you've, or maybe you have or haven't noticed that the using an equation of motion together with key events which cause parameters of that equation of motion to change actually creates a more continuous model of the movement than a time step, in which, if you think about it, a time step is literally has the same issue with state trajectories as discrete event, except that it applies it to every state. So in a time step model, typically the state is the location, but the thing is, it moves from one point in time instantaneously to another point in time in the future. That's exactly what we do when we schedule an event. And so where is the unit in between those two time points? And the answer is that you can't answer that. Because you can't ask that question in a time step world. In a time step world, you can only ask about the state at these discrete time points. You can't ask about it in between. I mean, you can try by putting Band-Aids on, but those Band-Aids do a number of things. One is they will fix a specific problem, which is why they're Band-Aids, but they typically create other problems. So, and I'll try not to. I'll try to get off the soapbox. Anyway, so got the movement piece down, at least for our basic equation of motion, which is a constant velocity, which, in itself has some issues in terms of being literally not the way things work. I mean, every real unit that moves, say from a standing position to let's say a cruising speed, has to go through some intermediate steps. And this model isn't doing that. This model is assuming you can kind of instantaneously go to cruising speed right away. That's an assumption, and then it's important. I hope maybe you're getting the meta message of that is, regardless of what model you're using, it's important to be upfront about your assumptions, and even to a fault. We've been doing that since the beginning, so even in our multiple server queue case, if we're modeling, say, a ticket line at the airport, where you kind of wait in a line, and then when the next station's available, you move there. We typically don't model the time it takes to get from the line to the server. And, it gave a reason why that was reasonable. That may not be a reasonable thing. If you have to travel a long distance to get to the server, then that needs to be modeled. But if, in this case, the time it takes to get from the queue to the server is relatively small compared to the time it takes to get the service and the time between when the arrivals come. In other words, compared to the magnitude of all the other quantities in the model, it's negligible. And if it isn't negligible, then that's something that needs to be addressed. And even if it's addressed, I mean, the other lesson I hope you're taking from this goes back to the statement, every model is wrong. Every model is wrong. And what that means is that every model, no matter how detailed you make it, no matter how, how much stuff you put into it, there are going to be things that it leaves out. And the hope is, I mean, you're not going to leave out something which is going to affect the reason you're doing the model in the first place. And what those reasons are, of course, differ depending on what you're using that simulation for. Here, what these models are mostly good for is analysis, namely answering a question that you don't know the answer to. And if you knew the answer, there's no point in building a model. If your purpose is to facilitate training, for example, in some of the other classes that you're encountering, then there's an entirely different set of criteria. The fidelity, the realism that you need in order to have a positive training environment, it becomes much more important than it does here. And even there, all of those models are wrong too. So, okay, so we have things that move around, and we've seen kind of the framework that I think is a fairly powerful one, is having one component, the mover, that does that one maneuver, and then another component that we've called a mover manager, sort of manages the movement. We can call it the decider or the commander or whatever you want to call it. But what I hope you can see how powerful that is, in the sense that without touching any of the mover code, if I want a different rule for how you're going to move, then all I need to do is just sort of unplug the other one and plug in a new one. And it's very, I mean, there are many different ways that you can do that. Many different rules. So for example, I don't know if we're going to get to it here, but so for example, supposing my unit is like a let's say a UAV that's kind of patrolling an area, kind of looking for something coming in. And then when it comes in, then it wants to kind of do something about it. Or maybe it's like patrolling an area, but then when it finds something that's of interest, maybe it might kind of move towards that thing that it found and engage it in some way. Well, that's an entirely different rule. That's it. And in fact, what you can actually do is you can kind of have kind of pluggable mover managers. So it's like if I'm in patrolling mode, I'm kind of doing this, but then if I'm in intercepting mode, then I kind of go to that. And then when I'm finished doing all that, then I go back to patrolling. So for example, I mean, there was an interesting model a student of mine did a few years ago about, it was looking at patrol boats that were kind of, patrolling a high value unit that was potentially being attacked by like small things. And there were some very interesting things that came out of that model. But again, what that involved, it involved sort of a patrolling context and an intercepting context. So, okay, so now what does it take to kind of do something like, say, intercept a potential target? Well, first you need to see it. And that's what we're kind of looking at here. And so it's like, can we do that? And the canonical sequence is this, just as a reminder. So the outer, we have events. We have the start move event and the end move event. And I know at least some of you were kind of thinking this when this was being covered, even though nobody sort of said it out loud, but I'm sure at least some of you were thinking, well, because the events, the start move event and the end move event, it seems like the unit just all of a sudden transports to the end. Just sort of pops up there. What if something happens in between? That's what this is addressing. So something can happen in between. But of course, if the thing is, if nothing happens in between, then why would you need to know where the thing was? In other words, if you remember, there was one, like say, if the unit was, supposing the unit kind of went like this, and this was the only other possibility. Well, as we've seen, that in this case, we can determine when that start move event occurs that no interaction will take place on this. And so when it reaches, there is no reason to even know or care where the thing is in between if this isn't, you know, if there's not going to be anything like this. And so, whereas I can't help myself, in a time step model, it's like you'd be going, do you see me now? 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 Okay. So there are two sets of events that we're concerned with, and today we're going to hopefully finish up with two of them, the two outside ones. And that is the idea of in this canonical sense, if we have a sensor that's stationary at the origin, in this case, it would have a circular footprint, and just FYI, if the footprint is something different, because, again, particularly radar-like things, or often have these kind of strange footprints. But if you can describe those, you again typically using things called splines, then it turns out you can apply all of this. It just gets more complicated. So doing the simplest possible thing. And the two things are as long as you're outside the possibility of the sensor detecting you, then then really the only interesting thing the only interesting event would be when, if any, does it actually enter the range, that is, go into a state where it could potentially be detected. And that's kind of what we're after. And then, assuming nothing bad happens in the in-between, if you kind of keep going, in this case, kind of completely cutting through the cookie, as it were, at some point you're going to leave. And once you leave, then there's, while the target is inside the range, then there's a possibility of detecting it, because now it's responding to the energy, whatever energy pulses there are. And then once it leaves, then it's out of range. And so no matter what you're sending out there, it's nothing can possibly happen. And, the thing is, as we've seen too, it's like if we're out here, if the next move kind of goes like that, then again, the computations will show that we don't have to do anything more on that. What's valuable about that is that although we spend a little bit more on these figuring this out, once we're in the maneuver, if there's no further, as long as this motion is in effect, then there's no event to schedule. So in other words, as far as the simulation is concerned, we're not spending a single CPU cycle worrying about anything that could happen, because we know it can't. Okay, so this was all from the other day. And so in order to schedule those events, we need to figure out when does, mostly it's when. When can we schedule that? And those times are based on the fact that, again, if you look, the green points where it enters and exits are all exactly our distance from the origin from where the sensor is. And those are the only two times, in this sequence, those are the only, every other place, it's not going to be equal, it's going to be something else. So if we solve our equation of motion equal to the radius of the sensor, then we come up with a quadratic formula And this is the result, so. And for the interested student may kind of try to derive this as well, but you don't have to. And, and it's like that, this is one of these things where it's like you don't really need to necessarily, I mean, like when I've been working with this for a while, I think I can remember it. When I haven't seen it for a while, but maybe that's my age too. So, the three things that happen when you get older: start to lose your memory, and whatever those other two are. Okay, so what are the possibilities? Well, one is we have two positive roots, and in which case we schedule the enter at the lower time. If we have a negative and a positive root, we schedule the exit at the one positive. And if they're negative, then we're moving away, we do nothing. And if we have complex roots, that means we totally miss it. We do nothing. And okay, so for the situation where we have a sensor which is stationary at the origin, then we have completely solved it. So now, let's look at an example. So I get to kind of choose the numbers so that I don't have to do as much work. When I make you do it, I think I'm a little meaner, but that's my problem. Okay, so we have a target. Okay, we have a stationary sensor at the origin. Oops. So we have our target is going to be at minus 30, 40 with a speed of 40. Its destination is going to be 50 minus 20. And so, roughly what's that going to look like? So our sensor, our sensor is going to be at the origin, but we're going to be at minus 30, 40, which is going to be maybe up here. Our destination is like 50 minus 20, so that's going to be maybe right here. And so our trajectory is going to look roughly like this, and it's always useful to kind of just draw rough pictures just to make sure you don't go crazy. And the sensor range is, I don't know exactly where it hits, but the sensor is at 20. Okay, so first we need to find the equation of motion of the target. And so we're at minus 30, 40, moving to 50, minus 20 at a speed of 40. So find velocity, that's usually, it takes 3 steps. So we take the difference between the destination and our stop location. And so that would be 50 minus a minus 30, that's 80, minus 20 minus 40, that's a minus 60, which is this. And then we want to find the magnitude of that, because we want to turn the whole thing into a vector in that direction with the magnitude of a speed. So in order to first turn it into a unit vector, we need to take that difference, take the Euclidean distance, which is the square root of the sums of the squares. And since I got to pick the numbers, it turned out to be 100. It usually doesn't work out that nice, but and also that's okay. So I get to cheat, you don't. Okay, so now our velocity is we multiply that. We take our unit vector, which is take that the big vector divided by its distance, multiply it by its speed, and we get 32 minus 24. So again, usually it's not so nice. Unless you, it's kind of, there was a guy walking through the forest and he sees a tree with a target on it and there's an arrow right in the bullseye. And then he walks a little further, he sees another tree and there's an arrow right in the bullseye. And after about 4 or 5 of these, this guy's an amazing archer. And then he finally finds the guy and he shot an arrow into the tree and was carefully drawing the target around the arrow. So that's what I get to do. Okay, so So that's our velocity. Now, what we want in the equation is the square of the magnitude of the velocity in addition to that. Again, that's just the Euclidean distance, which is turns out to be 1600. That is the square of the difference. Pardon me? Square this, yeah. Exactly. That's the easy way. Yeah, yeah, this is always just the square of the thing. So. But we do need the velocity to do this inner product. And that turns out to be minus 1920. And then we need the square of the magnitude of the location of its initial location, and that turns out to be 2500. See, this half shouldn't be there. That should be like this. Okay, and then okay, then the next thing to do is to figure out whether or not we need to even do anything more, which is to find the determinant. In other words, if the value of this expression under the radical is negative, then we're in complex territory and we can stop working. Now, you might want to, now, is it possible that this could be negative because there are a whole lot of squares? You know, so this can't be, this, and even this are all going to be positive. But the question is, what about this difference? And so if we start outside of the range, this is going to be negative. Is that clear? Because if we're outside the range, I mean, our range only went to here, and our distance is kind of longer than that. So that's so this could be negative. And is it enough negative to kind of overcome this? There's kind of a nice geometric interpretation of this, which has to do with the fact that the inner product can also be represented as the cosine of the angle between the vectors. And the thing is that if I'm out here, let's see, if I'm here and I'm kind of roughly headed towards the sensor, then it kind of looks like we have an acute angle, but in fact we have an obtuse angle. Because look, this vector, even though it's kind of based here, just as a vector, is really down here. And so for this, we have an obtuse angle, and the cosine of an obtuse angle is negative. And so this inner product is going to be negative in that situation, which kind of accounts for this minus out in front. So if this quantity is positive, then this quantity is going to be negative. But if this quantity is positive, that means it's kind of, we're actually moving away from the sensor. But if we're roughly moving towards it, kind of, then it's going to be negative, and so negative and negative is going to be a positive. And we're going to see that when the numbers kind of show up. But just as a, you know, so here we have here's the inner product, minus 30, 32, 40, minus 24, and that's a minus 1920. So at least we have a positive thing there. The magnitude of the, okay, we got that. And then now we can kind of basically compute that, and it's, I won't go through all the details here. Why? Because I was running out of room on the slide. So, but basically, okay, it's a positive, and so that means that we should continue. If this turns out to be negative, then you can stop. So we know we're going to have two real roots, and so let's figure out what they are. Well, first, here's that first part of it. So it's minus the inner product over the speed squared. So that would be 1920 over 16, which is in this case 1.2. And then unraveling these. So what we have is, well, when you unravel it all, we have, well, we computed the determinant already as this, but we need to take the square root divided by our velocity squared. And then that turns out to be about 1.3 something. So it's 1.2 plus or minus the 0.3 something. And then we have our two roots in this case. So the enter range is going to occur at this time. And so the question is, the next thing is, okay, where is the target? Well, you plug in any time that you're doing the maneuver, you plug that into the equation of motion. So our equation of motion is the velocity plus the time times, so it would be our starting location plus the time. Well, in this case, it would be the elapsed time, but we're starting at 0 in this case, times the velocity. So here's where we started. Here's our velocity. Here's the time we have, and then, so we get the coordinates of where it is. So why do this? Well, when you're implementing this, how do you know that it's doing the right thing? Especially in this case where it's, we've seen the implementation of the mover. Tomorrow we're going to start looking at how to, we're going to do the simplest implementation of dealing with the sensor. We're going to kind of put aside for the time being the detection, the actual detection piece, because there are some issues about how to, about the implementation itself. But if you're implementing it, then what you want to do is, again, be a scientist about it, which is to hopefully have verified these computations. If you're comfortable with programs like MATLAB or Mathematica or those things, you can actually code in these equations and then plug in the numbers without having to kind of worry about, and then ask it to solve the, instead of trying to plug in the equations, you can sort of ask it to solve the quadratic for you. So there are ways of doing that. So, but the point is that you have a numbers with which you test it by. And in fact, in kind of putting something together for your consumption, I tested one against these numbers and discovered that I had inadvertently switched a couple of coordinates somewhere because I wasn't, for the first pass, of course, it didn't work. And I'm going, okay, what the heck? Anyway, okay, so. All right, so now here's the thing is that what we have done is we have solved the case where the sensor is stationary at the origin and the target starts moving. And if that's all we could do, it wouldn't be of much use. So the question is, what if they're both moving? So in other words, what if the target's moving? What if the sensor's moving? So what can we do there? Again, now all the movement in this is going to have the same equation of motion, that same linear one. Do we have to kind of go back to the beginning and do it all over again in that case? Yeah, exactly. Yeah. So yeah, the equation of motion for the sensor, we have the equation of motion for the target. But having worked this out, having come up with this magical expression, do we have to kind of go and derive another one if they're both moving? And you might guess, because of the virtue of laziness, is that having done it for this case, it turns out that you don't really have to do much more work for the general case. You don't have to work it out again. Why? Because if we're kind of looking down in a kind of absolute coordinate way, where we're kind of being the God's eye here and looking down. But if you're the sensor, if you're the sensor, then you're seeing everything from your point of view or your frame of reference. And from your frame of reference, you're stationary at the origin and the world is revolving around you. Kind of like my youngest son. From the sensor's frame of reference, it is stationary and everything else is moving. So even if, let's look at this situation. Supposing we have a stationary target and we have a sensor that the target stays stationary, but the sensor starts moving, at least from our absolute God's eye perspective. If you're the sensor, though, what do you see? Yeah, you see the target moving towards you. In other words, from the sensor's frame of reference, it's stationary and the target is moving, even though from our frame of reference, it's the other way around. So in this situation, as long as we can unpack what the relative equation of motion is between the sensor and the target, then we're back to this situation entirely and the exact same equations apply. In other words, if both the target and the sensor are moving and the sensor isn't even at the origin, then if we do everything in relative coordinates from the sensor's perspective, then we are exactly in the same situation and exactly the same equation applies, just as long as we do everything relative. Okay, so let's see what that looks like in this situation. So again, we're assuming that the T naught is 0 still. And what I'll circle back to why even that is not a loss of generality. So let's say our target's equation of motion, we'll now put a subscript of T on the target. So it's the target location plus the target's velocity times the time in this case, because we're assuming the T naught is 0. In the implementation, we can't completely get away with that, but the sensor's equation of motion, okay, we'll put a subscript with S on it. So we have its location plus its velocity times its time. So we have those two equations of motion. Now, from the sensor's frame of reference, what we're looking at is the difference between the two equations of motion, which unravels to an equation which has exactly the same form as what we've been looking at, except now the sensor is stationary. So it's the difference between their location at the time we're starting this, plus the difference of their relative velocities times the elapsed time. And now all we need to do is apply the quadratic solution, taking our x naught as this relative location and our velocity as the relative velocity. All right, so let's apply it to this. So supposing the sensor now, let's have it move to say 30, 40 at a speed of 10. We'll let it. And the target is going to do exactly the same maneuver. So now it's not, I mean, now it's a little bit more uncertain. I know that if the speed were great enough, the sensor they would miss. But the equations would show that. In this case, I chose a speed of 10 just to make sure that they didn't miss. Okay, so what do you do here? Now we just have to unpack all the relative stuff. So we get the relative location, which is, here's where our target was. Our sensor is at 0. If this were not 0, we'd have to apply whatever that is. But again, the relative location is still, in this case, where the target is, but only because the sensor was at the origin. Okay, so now we need to do the same thing for the sensor's velocity. So its destination was 3040. So the vector difference was 3040. The magnitude is going to be the square root of the Euclidean distance, which turns out to be 50. And the velocity is going to be our speed, which is 10, times the difference over the magnitude. So that's 10, 30, 40 over 50. And so our velocity is 6 and 8. And sometimes it's helpful to kind of do a double check on this to see whether or not our, if there's been a mess up here, the magnitude would better equal our speed. So this would be 36 plus 64, that's 100. So that's 10 squared, check. Okay, so now we have the equation of motion of both the sensor and the target. And so we have the relative location, and now we need the relative velocity. And this can get messy. And you want to be careful. Like if there were radicals involved here, I encourage kind of holding on to them as much as possible and then only rounding off at the very end, because otherwise you can be way off. Okay, so the relative velocity is the target velocity minus the sensor's velocity. So that's 32 minus 24 minus 68. So that's 26 minus 32. Its magnitude is the magnitude squared is the sum of those squares, 1700. And the inner product now is, now we have it, so it's 26 minus 32 by minus 40, which was the relative location. And so that turns out to be minus 2060. So that means that there's a chance that we'll actually have a hit. Okay, so let's look at the determinant. Again, that's that magnitude velocity squared. So we plug in the relative values into the same equation. So again, we haven't done any more work other than the necessary work, which was to find the relative one. So we plug all that in. Again, we get a positive one, which we're going to have two real roots. We take, so they would be like basically root 6736 over 170. And so now we can go ahead and do the other one. So we've already computed the inner product. We have the square of the velocity. We have the negatives cancel. We get 206 over 170. And so the time is this, which is approximately this. So we have now we're going to enter a little bit sooner, and we're going to exit a little bit later, I think. But and so kind of where are they? So just looking at the enter range, now that this is sort of the where you have to kind of keep your finger on your place. If we say where is the target at the enter range, we have to back off from the relative equations and go back to the original equation for the target. That's where is the target at this time? Just plug in the time, and it turns out to be this. So that's where it's going to be. And you say, well, where's the sensor? Well, again, you plug in the time into the sensor's equation of motion, which was the origin plus the time times its velocity, which turns out to be this. So you can identify where there are going to be at the enter range. And you can also, if you wanted to, and I'll leave, if you say, where are they at the exit? Well, you can sort of plug that in and find the same thing. Is that all I have? Okay, so now, okay, so basically, why is this kind of it's necessary? Well, it's important to kind of know what the answer is when you're implementing this, to know that things are going to be happening at the right time. As I said, I discovered a mistake in one of my calculations, but only because I tested it against this and got different numbers. And so the question is, which is more fallible, my programming or my math? So they're both pretty fallible. And so we went back, triple checked the numbers. The numbers look good. Again, drew a picture. So, you know, you always want, you know, you don't want to totally rely on the numbers. So it's like the sensor was kind of doing this kind of thing, and the target was doing this kind of thing. And so what wasn't clear, like for the stationary one, you could actually kind of draw the picture and see that it actually did cross. For this, it was a little bit more iffy. But what you could do then is you could draw this picture with using the relative values that were computed before. Okay, so so now the next step is to try to implement all this, and because now what we haven't talked about yet is now what about these detection here? So for the first iteration, we're going to kind of punt on that a little bit and use what is called a cookie cutter sensor. You're familiar with what that is. You're sort of thinking of this as a cookie, and as soon as you step in, then you get detected, and as soon as you step out, you lose it. In practice, that's not the way actual ones work. The people who kind of work in the theory of this like cookie cutters because the math works out really nice. And you know, and so it's useful to kind of have it because it's fairly straightforward. But in fact, what you want in this framework is that I mean, it turns out that a couple things. One is in simulation, the quantities that we're interested in as far as detection goes are orthogonal to the ones that the people who study this come up with. The people who study detection theory and all that, typically the output of that is the probability of detection. Now, if you're running a simulation and I give you the probability of detection of this target against that sensor, how does that help you in the simulation? Okay, so I can tell you what, you know, so, but let's say, I mean, let's say I'm running, let's say a missile defense type of thing. And the effect of my countermeasures depend on, you know, how soon I detect it and when I can launch the countermeasures and kind of where they can intercept the potential target. So I need all that information. I need the geometry of the thing. Where the heck are they? Does the probability of detection give me any of that? Doesn't. And in fact, and this is often, you know, now think of a time step model. Okay, just I know I brag on them, but you know they have their uses. So even if we're running a time step model, and I say, okay, here's I give you the probability of detection. What does that mean? Does that mean, is that the probability that I'll ever detect it? Or is it the probability that I'll detect it at a given time step? And what's interesting is that usually, you know, again, because the people who do this are kind of all into the math and the equations, what you get is that they don't think of that. And that turns out to be quite problematic because, you know, again, just forget this for now. Let's say we have time step simulation. So at every step, we're going to say, okay, do we detect it or not? Because I want to know at what time step have I actually detected it, because I want to know where it is that I detected in time so I can do something about it. You know, and typically it's like you click the clock, you say, okay, is it detected or not? So there you would need a probability of detection at every time step. That would be a useful thing. But consider this. Supposing without making any changes whatsoever, I decide, well, you know, the time step I was using was maybe a little bit too big. I want to increase my fidelity by having a smaller time step. Now what do I do? If I use the same, you know, if my probability of detection is the probability of each ping, and I'm taking a ping at each time step, I'm now doubling the number of pings I'm taking, but I'm using the same probability. So if I were, you know, let's say I have a 50-50 chance of detecting something, or let's say, you know, just let's assume they're independent, just to make it simple. You're basically flipping a coin let's say you're flipping a coin every second. And if it comes up heads, you detect it. And so I'm flipping until I get a heads. But now I'm going to flip a coin every half a second. And now, basically, I'm sort of doubling my chances, but I haven't done anything. All I've done is change the time step. So in other words, the size of the time step can affect what the ability of the sensor to detect the target is. And that should be troubling. So the point is, the probability of detection, unless you marry it with a time step like that, and unless you adjust it in certain ways, for the simple situation I described, you can actually fix it. Basically, if I have my time step, I just have to have my probabilities, and then it all kind of works out, just because of the math of the thing. But they're more complicated ones, like they're these sort of wedding cake type of things, where it's like at a certain range, there's one probability that once I come into another range, there's another probability, and then as you come in closer, there's another. And in those cases, I mean, I literally saw this in a model, not a model that people were actually kind of, was kind of out there, and had the ability to do that, and also the ability to change the time step. And they said, oh, well, if you change the time step, then you need to kind of fix these range probability things. But they didn't say how. And as far as I know, nobody knows how. So, okay. But so here, when you start going into it, for the simulation perspective, we don't care about the probability of detection. We want to know when do we detect it and where the thing is at the very least. Any more complex things, it's like, okay, what else do we know about it? Do we identify, classify, blah, blah, blah. You can get into those weeds. But the important thing is when and where. And so instead of kind of going that route, why don't we directly model the when and where, the when at least. So in other words, if I can model what this is, I can figure out what the time is between when I've entered the range and the time when I detected it. And if I can come up with a model of that, then, then I can start having something which is useful in our discrete event model. And in fact, as you can see, for a cookie cutter, that time is 0. The time is 0 if we're a cookie cutter. But if we're not a cookie cutter, that's going to be something else. That could be typically a random variable. And in fact, what we'll eventually see is that for the situation where we have, let's say, a constant probability of detection, but with a quote time step like thing, then there's a corresponding, we can actually unravel that to something which actually works and is useful. But that is all to come. anyway, so tomorrow, though, I'm gonna start looking at, we're gonna punt on the detection thing for a little bit, and then, but then kind of see how we can implement all of this in the simplest possible setting. I'm gonna do the simplest one, and I'm gonna make you do the more complicated one, because that's my prerogative.